Hey guys, we are now starting section 6.3, which is about all of the properties of trig functions. So to get started, we have to remember that we have redefined each trig function using the coordinate plane and relating an angle to a point on a circle. So here are all of their new definitions and ratios again. This is how the trig functions relate to a point on any circle. But remember, the unit circle is the best because his radius is 1. So on the unit circle, the cosine is just x because it's x over 1. But this is how the trig functions relate to any point on any circle, okay? All right, well, in section 6.3, we have to learn the properties of each trig function. So we have to learn their domains, their ranges, their periods, all of their behavior, basically. So I need you guys to understand that the trig functions are known as periodic functions, which means that after a certain amount of inputs, the outputs start to repeat. The amount of time it takes to repeat is called the period. The problem is that some trig functions start to re-put outputs faster than other trig functions. So a couple of trig functions will have different periods than the other trig functions. But first, let's think about why the outputs start to repeat. Why do these functions start to repeat outputs? Well, think about it. These trig functions are functions of an angle, which means they depend on an angle that is being plugged into them. So eventually, as you rotate around the circle, angles are going to start to land in the same spot, and therefore the outputs will start to repeat ratios or outputs. So guys, for example, look at your unit circle. Okay, look at 30 degrees. If I asked you, what's the sine of 30 degrees? Well, on the unit circle, the sine of 30 degrees is represented by the y-coordinate. So the sine of 30 degrees is 1/2. Well, if I rotated all the way around the circle, 360 degrees, now I would be at an angle that is 390 degrees. So if I asked you, what's the sine of 390 degrees, you would also have to say it's 1/2. So as you rotate around, angles are going to start to land in the same spot. So an angle that lands in the same spot is going to have the same cosine and sine. I mean, if I asked you what's the cosine of 30 degrees, it's root 3 over 2. Well, what if I asked you what's the cosine of 390 degrees? Well, go all the way around, 390 degrees lands in the exact same spot as 30. So that means the cosine of 390 degrees is the exact same as root 3 over 2. So that's kind of how the sine and cosine functions work. So let's look at the sine. So since the sine function and the cosecant, right, his reciprocal, the sine and the cosecant, right, they depend on a y-coordinate and a radius. A y-coordinate and a radius is what the sine and cosecant function rely on. So you need to notice that if you start going around the unit circle to look at all of these angles' sines, well, look at all the y-coordinates. 0, 1/2, root 2 over 2, root 3 over 2, 1, root 3 over 2, root 2 over 2, 1/2, 0. None of them have started to repeat in a pattern yet. None of the y-coordinates have a set pattern yet. They're all different, right? I started at 0, and then I'm working my way around. None of the y-coordinates have actually repeated in a pattern. So now it's like, oh, I'm going to get 1/2 again. But it's negative 1/2, and it started there as a positive. So still, as you work your way around the circle, the y-coordinates are still not repeating. So if they're not repeating, they're not going to start repeating in a set pattern until you get all the way around. So the sine function and the cosecant function, who depend on the y-coordinate, they don't have a set pattern until you rotate all the way around. So the sine and the cosecant function are going to have a period, if you will, of 360 degrees. You have to rotate all the way around before the y-coordinates, the outputs, start to repeat. So the period of the sine and cosecant is 360 degrees. However, we always give the period in radians. So you have to make one complete rotation before the outputs start to repeat. So that is 2 pi radians. So the period of the sine and cosecant function will be 2 pi radians. Well, guys, now let's look at the cosine and the secant function. The cosine And the secant function, well, the cosine and the secant function, they depend on an x-coordinate and a radius, right? Well, if you start looking at your unit circle, look at all the x-coordinates, right? The x-coordinates represent all the cosines and all the secants, in a way, a ratio of them, or a reciprocal of them, of all these angles. So if I start with all my x-coordinates, I get 1, root 3 over 2, root 2 over 2, 1/2, 0, negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1. None of the x-coordinates are repeating in a specific pattern yet. And even when I get here, they're still not repeating because he started as positive and this one's negative. So now I go all the way around 0, 1/2. Again, there will not be any repeating of these ratios. The x-coordinates will not repeat until you make one complete rotation. So that means that the period of the cosine and the secant function is going to be one complete rotation, which is 360 degrees. But again, they want the period in radians. So one complete rotation is 2 pi radians. So that means that the period of the cosine and secant function will be 2 pi radians, one complete rotation until the ratios start to repeat. There's a pattern, or the outputs start to repeat. All right, but, big but, the tangent and the cotangent function, their ratios don't just depend on x and a radius or y and a radius. Their functions depend on a y coordinate and an x coordinate and a y coordinate. So you're going to notice that actually, because they don't just depend on just x or just y, they depend on both the x and the y, their functions actually start to repeat outputs faster. So watch, tangent is a y coordinate over an x coordinate, right? Okay, so if you go around and you start throwing all of the y coordinates over an x coordinate, well, 0 over 1, right? That's 0. 1/2 over root 3 over 2. Just hang on to that. You don't have to clean it up. Just think of it as 1/2 over root 3 over 2. Root 2 over 2 over root 2 over 2. Root 3 over 2 over 1/2. 1 over 0, that'll be undefined, that's okay. Now you plug this one over, right? So now it's root 3 over 2 over negative 1/2. So again, when I'm throwing all of my y's over my x's, there's no repeat in the output that I get yet. None of the y's over x's match yet. Okay, but when you start getting here, right, now you're going to get 0 over negative 1. Well, 0 over negative 1 is 0. Well, 0 over 1 was 0. So that means that the tangent at 0 degrees is the exact same ratio as the tangent at 180 degrees. They're both a ratio of 0 over 1 or 0 over negative 1. So that means we have a ratio that has popped up again. He had a ratio of 0, he has a ratio of 0, and they're 180 degrees away. Well, look at here, right? If you notice across from him, I would have originally at 30 degrees taken 1/2 and put it over root 3 over 2. Well, if I put a negative 1/2 over a negative root 3 over 2, a negative over a negative becomes a positive. It'll be the same ratio as this y over that x as this y over this x. So now, how many degrees away are 30 degrees and 210 degrees? They're 180 degrees. So now if you go to the next one, look here, across from him, I would have put root 2 over 2 over root 2 over 2 to get the tangent of 45 degrees. Well, to get the tangent of 225 degrees, I'm going to put a negative root 2 over a negative root 2. So guess what? A negative over a negative is going to reduce to a positive. So this y over that x is the same ratio as this y over that x. So 45 and 225 have the same tangent ratio. And how many degrees away from each other are they? 180 degrees. So that means that the tangent function starts to repeat outputs after 180 degrees. So the period of the tangent function is going to be 180 degrees, which is pi radians. Every pi radians, the outputs will start to repeat that come out of the tangent function. And it's the exact same thing for the cotangent, because now the cotangent, you're going to put x over y. But it's the same thing. His x over his y is the same ratio as this x over that y. So the cotangent is also going to start repeating outputs, repeating ratios after 180 degrees. So the period of the tangent and the cotangent function is going to be 180 degrees, pi radians. So they repeat faster than the sine, the cosine, the secant, and the cosecant, okay? So just remember that they have a faster period. So let's fill that in. So the period of each trig function is, well, like I said, the sine function's period is you have to make one complete rotation before the outputs start to repeat. So one complete rotation is 2 pi radians. All right, which means that his reciprocal trig function is also going to have a period of 2 pi radians. It'll take a complete rotation around before the outputs start to repeat, okay? Well, what's the period of the cosine? How far did we have to rotate until the cosine started repeating outputs? We had to make one complete rotation before the x-coordinate started to repeat. So his period is 2 pi radians, a complete rotation. Well, the secant, his reciprocal function, again, the x's don't repeat until you make one complete rotation. So then that means 1 over x, 1 over the cosine, is also not going to repeat until you make one complete rotation, which is 2 pi radians. But the tangent and the cotangent, right? They are going to have a faster period. Their outputs repeat faster than the sine and cosine and the cosecant and secant. They started to repeat outputs after 180 degrees, which is pi radians. So they have a period of pi radians. Well, the cotangent, which is his reciprocal, same thing. If I start putting the x's over the y's, they actually start to repeat outputs after 180 degrees, which is pi radians. Okay? All right. Now, I also want you to notice that some trig functions have angles that make their ratios undefined. So if I go back to my unit circle really fast, where's my unit circle? Right here. Well, guys, look at it. If you go around your circle, your sines and cosines to all of these angles were literally the x and y coordinates. So they all had ratios. The sines and cosines all had definable ratios. They're written right here on the circle. But if you notice, the cosecant and the secant, they are reciprocals of these x and y coordinates. So if you start to reciprocate coordinates that are 0, so for example, the sine at 0 degrees was 0, the y coordinate. But the cosecant at 0 degrees is the reciprocal of 0, which is undefined. All right, if I went up here and I asked you what's the cosine of 90 degrees, well, the cosine of 90 degrees is 0. It's the x-coordinate. But the secant of 90 degrees is the reciprocal of 0. And the reciprocal of 0 is undefined. So the cosecant and the secant are going to have angles that spit out an undefined ratio. It's the same thing with the tangent and cotangent. If I asked you what is the tangent of 90 degrees, the tangent of 90 degrees is y over x, 1 over 0. That's undefined. So that's an angle that you shouldn't be plugging in to the tangent function. If I asked you, well, what's the cotangent of 0 degrees? Well, the cotangent of 0 degrees is supposed to be the reciprocal of tangent, right? So not y over x, but x over y. Well, what's 1 over 0? Undefined. So the cotangent and the tangent function are also going to have angles that spit out undefined ratios. It is only the sine and cosine function who never spit out undefined ratios, okay? All right, so let's write that down. So therefore, some trig functions will have restricted domains. So the tangent, the cotangent, the cosecant, and the secant function have restricted domains. That means that sometimes you can plug an angle into one of these functions and an undefined ratio comes out. So we have to be careful with them. And that is all things you have to know when you go to write down what all of their properties are. So I'll do that in the next video.